Hello learners, I am Dr. Nidhi Mathur, PhD in Public Administration and teaching at Institute of Management Technology, Center for Distance Learning, Ghaziabad. The subject expert is Dr. Nidhi Mathur, teaching in National Law University, Jodhpur, Rajasthan. Previously, we discussed the decision theory of operations research as applied in the business scenario. Our topic of discussion for today is the Markov analysis. Let us understand the meaning of Markov analysis. The process in which the current behavior of a given variable is analyzed in order to predict the future behavior of that variable is called as Markov analysis. It is a method of forecasting the future value of a variable whose predicted values is influenced only by the current state. In other words, predicting a random variable based solely upon the current circumstances and not by any prior activity is the true essence of Markov analysis. A Russian mathematician named Andrei A. Markov earlier in this century developed this technique and introduced the study of stochastic process, which are processes that involve the operation of chance. He used it first to describe and predict the behavior of particles of gas in a closed container. A new sequence of random but related events which look similar to the original can be generated with the help of Markov analysis. Dependent random events, that is, events that only depend on what happened last, can be analyzed using this analysis. A probabilistic technique that helps in the process of decision making by providing a probabilistic description of various outcomes is Markov analysis. Terminologies. Stochastic processes. This process is used to study the dynamics of a given system and deals with the collection of a random variable indexed by some set. Independent events. If the occurrence of an event has no interrelation with its previous outcome, then these occurrences are stated as independent events. One of the best examples is of flipping a coin, as every time we flip a coin, the result could be head or tail, and that is independent of the memory of what happened in the last flip, and hence they are independent events. Dependent events. If the outcome of one event affects the outcome of another event, then these two events are said to be dependent events. Random variables. If the value of a variable depends upon the outcome of a random experiment or phenomena, it is called as a random variable. Steady state probabilities. After a large number of periods, the probability of the system being in a particular state is independent of the beginning state of the system. These probabilities that are found after several transitions are known as steady state probabilities. Understanding Markov model. A stochastic based model used to model randomly changing systems is called as Markov model. The basic assumption in Markov model is that the future events will depend only on the current scenario of the present event and not on the past activity. The probabilities of the future event for decision making acts as a result. Given the current state of a variable, the Markov analysis process involves defining the likelihood of a future action. A decision tree can be drawn and the likelihood of a result can be calculated once the probabilities of future actions at each state are determined. Numerically, the relation is defined as P next period is equal to P current period multiplied by transition probability P. The following assumptions are made in Markov model. The sum of the probabilities of moving from a state to all other states is always 1. The probabilities are applicable to all system participants. The probabilities are constant over time. The states are independent over time. Now, let us have a set of states S equal S underscore 1, S underscore 2, S underscore 3, S underscore R. The process starts at one of the processes and moves from one state to another successively. If the system is currently at Si, then it moves to state Sj at the next step with the probability by Pij, and this probability does not depend on which state the system was before the current state. P equal P1, P2, P3 and so on till Pr be the probability matrix of each step. For such probability matrix, P1 plus P2 plus P3 and so on. Pr is equal to 1 and let Pij equal P11, P12 till P1r, P21, P22 till P2r, PR1, PR2 till PRR be the transition probability matrix. For non-repairable systems, Markov analysis requires component failure rates to be assumed and repair rates for repairable systems, just like all quantitative methods in reliability engineering. These rates are used by Markov analysis within a mathematical model that includes all of the possible states of a system, and within this model the failure and repair rates represents the rates of which the system makes transitions from one system state to another. Therefore, failure and repair rates act as transition rates within the model, which is called as Markov chain and more accurately described as a network of interconnected states. Interconnection is present between two states in the network. If a transition, that is component failure or repair, leads from one of the states to the other, it can be stated that looking at the network of all possible states of a system, that is the state space of a system, where transition rates between these states are determined by the failure and repair rates of the components, is what Markov analysis does fundamentally. The basic assumption in the simplest model or network is that the components can be in just one of the two possible states, either failed or working. Therefore, a system with the n components can be in any one of 2 raised to the power n possible states. Therefore, the transitions in the simplest network takes place according to the failure and repair rates of the relevant components, and the network has 2 raised to the power n states possible. The state space diagram is an example of a 2-component system. There is one further assumption within the model on which Markov analysis depends. This assumption is that transition rates between the states of a system do not depend on the states that the system has been in. Usually, it's assumed that the transition rates are constant and don't change over time. This means that the time for any given transition to take place has an exponential distribution. The unique feature of an exponential distribution is that it is memory-less, in the sense that a given transition does not become more or less likely as time passes. As a consequence of this constant transition rate feature, the future of a Markov system depends purely on its current state and not on the historical transitions by which it has reached its current state. It is this feature that gives the memory-less characteristic of Markov systems. Mathematically, this characteristic provides huge benefits in terms of simplifying the analysis of a system and enables the precise reliability or availability to be calculated. This has particular application when the effects of a small design changes need to be quantified, or where design changes for high integrity systems are investigated. Monte Carlo simulation can often be ineffective in such situation where Markov analysis is ideally suited, provided that the underlying assumptions of a Markov system described are satisfied. Even if the exponential distribution does not accurately represent times to transition, the results of a Markov analysis can be surprisingly accurate, especially when assessing the effects of small design changes. Applications of Markov analysis. Markov analysis is a method that can be applied to both repairable and non-repairable types of system. Before the system moves or transits from one state to some other distinct state, the average time spent by the system in each of its distinct state is the basic output of a Markov analysis. For example, if the system suffers a component failure or if a repair has been carried out, then such a transition or change of state will occur, and in both the cases a distinct change in the state will have taken place. A complete description of the system in terms of its reliability, availability and resource utilization, such as use of maintenance teams, spares holdings, buffers, etc., can be obtained from the output of Markov analysis. By comparing the reliability and availability performances of design under consideration and the effect of small tweaks made to them, different system designs can be explored. To identify the optimal design choice, the results produced by Markov analysis can be used for analyzing cost benefit. Markov processes are often applicable to decision problems as a special class of mathematical models. The various states are defined in Markov process, and the probability of going to each of the states depends only on the present date and is independent of how we arrived at that state. The real life business systems are very dynamic in nature. and to design a probabilistic model that can capture everything is not an easy task for market researchers. As a business process evolves, more sophisticated models are required by researchers to understand customer behavior. Stochastic process is a probability model for the business process which grows over the period of time and describes the consumer behavior. Markov chain is one of the techniques to perform a stochastic process that is based on the present state to predict the future state of the customer. As a management tool, wide variety of decisions situations benefits from successful application of Markov analysis. Examining and predicting the behavior of customers in terms of their brand loyalty and their switching from one brand to another is perhaps the widest use of this analysis, and it is used as a research tool for examining and forecasting the frequency with which customers will remain loyal to one brand or switch to other. The general assumption here is that the customers will choose to buy brands in the future that reflect their choices in the past rather than randomly shifting from one brand to another. Hence, it helps in forecasting future brand loyalty of current customers and how the company's market share gets affected from the outcomes of these consumer decisions. Markov analysis is also incorporated in some stock prices and options prices forecasting methods. Another important practical application of Markov analysis in the business world is to predict the number of defective pieces that will come off an assembly line given the operating status of the machines on the line. Markov analysis also helps in predicting the proportion of bad debts out of companies' accounts receivables. Apart from all the above mentioned applications, Markov analysis can also be found in models such as a model for manpower planning, a model for human needs, a model for analyzing internal manpower supply, a model for scheduling hospital admissions, a model for assessing the behavior of stock prices, etc. Real-time examples. To understand the real-time implementation of Markov analysis, we can consider an accounts receivable example. Say in the accounts receivable department, accounts are in one of the states or categories: state 1 S1 paid, state 2 S2 bad debt or overdue more than 3 months and company writes off the debt, state 3 S3 overdue less than 1 month, state 4 S4 overdue between 1 and 3 months. Here the states are mutually exclusive and collectively exhaustive. There will be a certain fraction of accounts in each state at any given time. Say we have the percentage of accounts receivable in each state in the current period. We have a row vector of probabilities S1, S2, S3, S4 in general. Say now there are 25% of accounts in each state. We would have 0.25, 0.25, 0.25 and 0.25. This set of numbers is called the vector of state probabilities. The matrix of transition probabilities 1, 0, 0, 0, 0, 1, 0, 0, 0.6, 0, 0.2, 0.2, 0.4, 0.1, 0.3, 0.2. In the current period, the first row is being in the first state, the second row is being in the second state and so on down the rows. Now, let us think about each column in the matrix of transition probabilities. The first column says an account is in state 1 in the next period. The second column says an account is in state 2 in the next period, and so on. Note, the first row has values 1, 0, 0, 0. The values add to 1. If an account is all paid this period, then it must be all paid next period. So, the 1 means there is 100% chance of being all paid next period and 0% chance in being in any other category. In the second row, we have 0, 1, 0, 0. If an account start as bad, it will always be bad. So, it has a 0 chance of being paid, less than 1 period overdue, or be between 1 and 3 periods overdue. In row 3, we have 0.6, 0, 0.2, 0.2. If an account is less than 1 month overdue now, next period there is a 60% chance it will be all paid, 0% chance it will be bad because it can't be over 3 months bad, 20% chance it will be less than a month. But the question here is that how can an account be bad less than 1 month now and less than 1 month next period? Any account can have more than one unpaid bill, and we keep track of the oldest unpaid bill for the category. Note that each row has to add up to 1. Now, if each state has 25% of the accounts this period, what percent will be in each state next period? We take the row vector as T, U, V, W and the matrix of transition probabilities as D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S. Now, we multiply them as follows: A1, A2, A3, A4 as A1 equal TD plus UH plus VL plus WP, A2 equal TE plus UI plus VM plus WQ, A3 is equal to TF plus UJ plus Vn plus WR, A4 is equal to TG plus UK plus VO plus WS. This implies 0.25, 0.25, 0.25, 0.25 multiplied by 1, 0, 0, 0, 0, 1, 0, 0, 0.6, 0, 0.2, 0.2, 0.4, 0.1, 0.3, 0.2. We will have A1, A2, A3, A4 as follows. A1 is equal 0.251 plus 0.250 plus 0.25.6 plus 0.25.4, which is equal to 0.5. A2 equal 0.250 plus 0.251 plus 0.250 plus 0.25.1 is equal to 0.275. A3 is equal to 0.250 plus 0.251 plus 0.250 plus 0.25.1, which is equal to 0.275. A4 equal 0.250 plus 0.250 plus 0.25.2 plus 0.25.2, which is equal to 0.1. Now, if we start with 25% of accounts in state 1, then the next period we have 50% of accounts in state 1 and so on. To find what the percentage in each state is, it would be 2 periods from the start and we would do the same calculation, but use the row vector that we ended within the first period 0.5, 0.275, 0.125, 0.1. To find the probabilities of being in each state at the end of 2 months, we would put 2 for number of transitions and would get 0.615, 0.285, 0.055, 0.045. Now, in this particular problem, all the states are absorbing states, that is, once reached that state, it stays in it, just like if once debt is bad, it is always bad. However, if we consider a long run scenario, the all debt either be bad or paid. No matter how many transitions are put, there is always an output section called matrices and includes the FA matrix. In the Markov analysis problem, that has absorbing states. Now, in our problem, we have 0.9655, 0.0345, 0.8621, 0.1379. Here the rows represent the non-absorbing states and the columns represent the absorbing state. The first row is state 3, debt of less than 1 month, and row 2 is state 4, debt of 1 to 3 months. Column 1 is paid debt and column 2 is bad debt. So, the first row says 96.55% of less than 1 month debt will be paid over the long term and only 3.45% of this debt will not be paid. The second row means that 86.21% of 1 to 3 month debt will be paid over the long term and 13.79% of this debt will go bad. Say that there is rupees 20,000 in the less than 1 month overdue category and rupees 15,000 in the 1 to 3 month overdue category. How much can the company expect to collect of this rupees 70,000 and how much will it not collect? Now, if we do matrix multiplication here, we have 20,000, 50,000 multiplied by 0.9655, 0.0345, 0.8621, 0.1379. We get 20,000 multiplied by 0.9655 plus 50,000 multiplied by 0.8621, 20,000 multiplied by 0.0345 plus 50,000 multiplied by 0.1379 or 62,415, 7,585. This means that out of rupees 70,000 in states 3 and 4, the expectation is rupees 62,410 to be paid and rupees 7,585 to go in bad debt. Advantages of Markov analysis. Due to the analytical nature of Markov analysis, it has advantages of speed and accuracy. In comparison to Monte Carlo simulation, the Markov analysis is faster and more accurate. It is easy to derive Markov model from successional data. All the essential parameters of dynamic change are summarized by the transition matrix. Over a period of time, Markov analysis provides deep insight into changes in the system. Disadvantages of Markov analysis. Markov analysis requires the model to be designed very carefully as Markov property assumptions may be invalid for the system being modeled. The estimated conditional probabilities in Markov analysis are based on the current state, and it often provides a very little information about why something happened. In a situation where the information of an earlier outcome is missing, Markov analysis can't be used to predict future outcomes. Markov analysis is a valuable tool for predicting the probability of a future outcome, but it does not provide explanation. In this, we discussed all about Markov analysis. It can be concluded with some of the highlighting points like Markov analysis is a method of analyzing the current behavior of a given variable in order to predict the future behavior of that variable. Special classes of mathematical models that are applicable to decision problems are Markov processes. If the predicted value of a variable is influenced only by its current state, Markov analysis method is used to forecast the value of that variable. Simplicity and out of sample forecasting accuracy are the primary advantages of Markov analysis. Markov models are to model the probabilities of different states and the rates of transitions among them. It is also used to recognize patterns, make predictions, and to learn the statistics of sequential data. So, that is all for today. Hope you have understood. We will meet in the next episode with a new topic. Till then, take care and goodbye.